Dear learners, welcome to week 4 lecture 2. In this lecture, I shall explain the membrane shell theory and moment shell theory. In previous lectures, we have completed that basic formulation and the special cases for spherical shell, cylindrical shell, then circular plate, rectangular plate. Now, before a generalized solution of a complete shell, there are two basic theories. One is membrane shell theory and another is moment shell theory. Already that in the lecture 1, I have covered that membrane shell theory is applicable to thin shells and it can take only the membrane loading, means it cannot sustain with the bending stresses or bending moments. Shell is thin and subjected to only in plane stretching cases. So there are number of numerous examples in which membrane theory of cells are applied. So since it cannot take any bending stress, so moments, whether you talk about M11, M22 or the twisting moment M21 and the shear forces Q1, Q2 are 0. Now we are saying that shell is thin, so zeta by R1 term can be neglected. If we do so, N12 becomes N21. So I have developed that out of 5 governing equations, only 3 remains for the case of membrane theory of cells. That equation number, in our case equation number 3rd and 4th vanishes because equation number 3rd and 4th contains moment and Q. So equation number 1, equation number 2 and equation number 3 is valid for a doubly curved shell, and you can find out a special cases like surface of revolution or a cylindrical shell. So substituting the corresponding parameters A1, A2 or R1, R2, you can get that set of equations for the membrane theory of cells. Now, what is the expression of strains for the membrane case? For the membrane case, there is no curvature, no bending. So, because no rotations are considered 0. So, only the stretching part, linear membrane part is considered. The zeta pi's double derivative is not considered, or psi comma x or psi comma y not taken care. Same way epsilon 22 and gamma 12. Again, because this capital A1, we say that shell is thin, so zeta by R2 is neglected. So it is replaced by a small a1, you see here, and kept it inside, and same way in the epsilon 22 and gamma 12. So these are the expression of strains. Epsilon 11, epsilon 22 and gamma 12 are taken care. Now we are interested in the expression of N11. The expression, the general expression of N11 is this. Now if you substitute the constitutive relations, that Q11 epsilon 11 naught plus Q12 epsilon 22 naught into d zeta, so then N11 give you this expression, because they are only a function of alpha and beta, not a function of thickness. So if you take the integration minus h by 2 to plus h by 2, d zeta gives you only h. So this h comes here. Same way the expression of N22 gives you this expression. So, if we further mathematically simplify, it becomes q11 epsilon 11 naught plus q12 epsilon 22 naught is equal to n11 by h, and q12 epsilon 11 naught plus q22 epsilon naught n222 by h. From here, we can express the value of epsilon 11 or epsilon 22 in terms of n11 or n22h. So, these are two equations, simple. So, just following that you multiply this equation by q12, this equation by q11, then they subtract from second equation from the first. So, from here the expression of epsilon 22 in terms of stresses can be expressed. Similarly, the expression of epsilon 11 can be obtained. So, q12 n11h minus q11 n22 by h, then q22 n11 by h minus q12 n22 by h upon make q11 22 minus q1 square. So, if you substitute for a isotropic case, q11 and q22 are E by 1 minus mu square and q12 is mu times E by 1 minus mu square. If you substitute that reduces to only 1 by EH. So, we can say that epsilon 11 is nothing but 1 by EH n11 minus mu times of n22. Epsilon 22 can be find it out 1 by EH n22 minus mu times n11 and gamma 12 can be find out 2 plus mu times of E and 2. You may be asking the question that why we are interested to find out epsilon 11, epsilon 22 and gamma 12. Because our ultimate aim is to find out the deflection or the strains in the body, and then if we are interested to find out the stresses. So, for that purpose, because our governing equation in terms of n11, n22 and n12. So, for this case if we somehow know this value of stress resultant, then we can tell that how much strain will be developed in that body. So, we have derived the expression of strains in terms of stress resultants. For the case of a composite plate, this will be in terms of like q11 will be E1 upon 1 minus mu 21 into mu 12 and q22 will be. So, the expression will be slightly complex like this. If you substitute those values, one can obtain the expression. Now, can we express those three equations depending upon our special cases, because ultimately we are going to solve a structural problem. So, very first maybe that cell of revolution, in which the generator may be a curved line. So, for that case A1, the Lamy parameter A1 is R1 and Lamy parameter A2 is either small r or capital R2 sin phi. If we have to take the derivative with respect to phi, then it will be r cos phi. Already in lecture 1 of week 4, I have explained that details are given that how it will be R1 will be there using some terminologies, and curvatures can be 1 by R1, 1 by R2. If you substitute these parameters, taking alpha is phi and beta is theta, these equations will look like this. So, here instead of a R2 sin phi, small r is put it here, so that equations looks clean, but later on when we are going to solve the problem, r need to be replaced by capital R2 sin phi. Similarly, can the governing equations for a circular cylindrical cell, A1 is 1, A2 is R, R1 is infinity, R2 is R. If you substitute these expressions, so these three equations we obtain that first equation is n11 comma x plus 1 by r n21 comma theta plus q1, Then second equation will be n22 comma theta by r plus n12 comma x plus q2, and third equations give you n22 by r plus q3 equal to 3. So, the solution of circular cylindrical shell is very easy, and in structural point of view, that most of the surfaces are made of circular cylindrical shell. So, it is a well researched area, so in which the structures are developed and the solution is easy. Definitely one can get the solution for that generalized shell of revolution. Even for that case we can develop the solution, but for an example point of view I will explain that how to solve this equation. So, from here a third equation can be directly says that n theta theta or n22 can be expressed in terms of, if loading is known to you, r times of that, and if you substitute here then n12 can be obtained, and if you substitute here then n11 can be obtained. So, in this way the first third equation is solved, then second equation, and ultimately the first equation, and that during that process if some constants comes they are find it out. So, it is written the three equations in proper way, that nxx, nx theta comma theta plus q1. So, very first application, that a closed cylindrical shell and under liquid pressure or liquid storage tank. So, if you say that there are cylindrical shells in which the LPG or some oil or any water is stored inside that tank, and a cylinder are filled with liquid and it is simply supported with the ends. So, we can directly utilize this set of equations. If you remember that very initially after developing the governing equation, I told that we have to convert into the basic primary variables, then we are going to solve. But for these type of cases, when we talk about membrane shell of theory, then it can be solved in terms of stresses itself. So, liquid pressure, let us say, so you say that Z is going upward. So, but pressure is acting inside that. So, we can write that Q3 can be written as minus of P naught plus gamma r cos theta. We have taken that pressure is acting in the negative surface normal of that. So, from there n theta theta by r minus q r, or in some of the books you can say that if you assume that it is acting P naught minus liquid pressure will be in opposite direction always. So, here gamma is known as specific weight of the liquid, and this is the component that when theta is 0 it will be equal to gamma r, when theta is 90 then it will be 0. So, there will be no pressure at the top of the liquid. So, in that equation if you substitute in the third equation it becomes minus of that. So, ultimately P naught minus gamma r cos theta. So, depending upon that initial assumptions, in initial assumptions basically in the third equation n theta theta by r, some are putting here q is 0 or some are putting plus. So, because of that surface normal the slightly change in this thing. So, from here n theta theta can be found it out. So, it is varying circumferential stress resultant will be P naught into r minus gamma r square cos theta. Now, from this equation if we substitute into the second equation where it is n theta comma theta. So, when you do cos theta will be minus sin theta and it becomes plus. So, 1 minus r of this, ultimately it will be r square. So, gamma r sin theta. Now, we have to integrate with respect to theta. If you integrate with respect to theta, it is acting as a constant minus x plus any function, because it is a partial derivative along x. So, f1 will be a function in the theta direction. Now we can substitute this expression in the first equation, and in the first equation nxx comma x equal to minus 1 by r nx theta comma theta. And if you take the derivative with respect to theta, it will be f dash theta. Again integrating with respect to x gives you this expression minus 1 by r f dash into x, because it is a function of theta only, plus f2 which is another constant function of theta. So, now here f1, f1 dash and f2 we have to find out. So, cylinder is simply supported. If something is simply supported, it means the axial force and axial moment. Now, we are talking about a membrane stress, the moment is not there. So, axial force is going to be 0. So, when you say that x is equal to 0 of a shell and x is equal to L, nxx is 0. So, if we apply this condition, then that if we put x is 0, this has become 0, this has become 0. So, f2 theta equal to 0, and if we put that x is equal to L, this is again 0, then f dash theta comes like this. If we integrate with respect to theta, then only cos theta becomes minus sin theta. Some integrating constant come up, but we say that it is not a membrane state of stress. So, this integrating constant is going to be 0. So, from here we can find out all the stress resultant in terms of a pressure, radius and length. So, they are varying accordingly. Now, we can say that sigma xx is equal to nxx by h. If divided by h, that will be the average stress. These are the average stresses, tau x theta, sigma theta theta and sigma xx. And after that, we have already derived the expression of epsilon xx, epsilon theta theta and gamma x theta. From there we can find out the strains in terms of, basically it was E h nxx minus mu times of n theta theta. Then epsilon xx, epsilon theta theta, gamma x theta, they are having a terms like del u, then v or w. So, from there these three equations, so we can solve displacements by integrating basically, because they are having some derivatives. Now, there are some other applications, that roof cell structures. When we design a roof of a building which is under self weight. So, the roof of a building may be a spherical dome or a cylindrical shell, or a, if you say that, a frustum kind of thing, conical shell or any other kind. Second application is liquid storage facilities. Third application is axisymmetric pressure vessels. So, when you talk about axisymmetric loaded dome roof or a spherical dome roof, then the main concept is that first we have to find out the component of loads. If we are correctly define the components of load, so problem is easy to solve. If the loading components are not defined properly, then it will be a problem, because once you know the loading, the equations are very simple. And further, for the case of axisymmetry, that in plane component of stress resultant 1, 2 and 2, 1 can be taken as 0. Next, that cylindrical shell. So, again that we have to define the components of loading and the boundaries that it may be simply supported x is equal to 0 and x is equal to a. So, from there one can find out the n theta theta and then nx theta and then nxx finally. So, the gist of this problem is that in membrane shell theory the loading component should be clearly defined, and then depending upon the case we can solve the problem, and the solution of a cylindrical shell is very easy. In that case it is first we solve a third equation and then second and first. So, for the case of cylindrical shell it is very easy and boundary conditions are satisfied in the terms of stress resultants. Now, there are the cases that there may be some mixed shells like cylindrical, spherical and some ring or conical shape. So, how do we get the solution? So, basically we have to find out the solution in 3 domains and then we have to club the solution. But at the joints the solutions will not be valid, because at the joints there will be a concept of that because curvature change. So, the stresses moments may generate at the curvature change point or the thickness, if thickness of shell is changing, let us say this thickness and here is small thickness like that, then also here. So, the membrane shell theory cannot predict the accurate behavior of all these junctions and the supporting structures where that the boundary conditions are expressed in terms of displacement. So, this type of designs how do we solve are given in detail a book by Thin Plates and Shell by Wenzel. So, some of you may be interested, they can go and see that how do we solve this kind of problems. So, you have aware that that membrane shell theory cannot give the solution here, then the concept of moment shell theory comes up and we can get the solution this here. So, for a complete structure we add it, means there are areas where membrane shell theory is applicable and areas where moment shell theory is applicable. So, it is a combination of those and then a design can be complete. If you do not consider the membrane shell theory, so your design is not reliable because at the joint it may have large amount of stresses. We need to assess it. Now, already said that the next is the moment theory of circular cylindrical shell. Why I am talking about only circular cylindrical shell? Because that moment theory is in general, if we apply, is very complex. So, we cannot get the solution for all cases. So, we have a analytical solution for typical cases. So, that solution for a circular cylindrical shell is possible for some cases. So, most of the time that circular cylindrical shells are used extensively for structural applications, and so locations where deflections are restricted, means the boundary conditions are expressed in terms of deflections. If you say that in case of simply supported we have satisfied only axial stress, we did not satisfy the W is equal to 0. If we have to satisfy the, let us say, clamped edge, that you say that my cylinder is clamped at some point, then your deflection is 0 and slope is 0. So, for satisfaction of that you need to use the, first of all, because at the clamped edge, yes, there will be shear force, there will be moment. So, it will not come into a membrane case, because in the membrane we do not assume shear force and moment or the horizontal force, all this. And next is there is change in the curvature, cylindrical to spherical or spherical to conical or some other kind. Membrane theory cannot maintain deflection and rotation compatibility between the shells. So, at these locations shear force, moments are generated and which causes a shear bending and shear stresses. But the important, very important observation, or I would like to say that point to be noted, that at the junctions, though the moments, shear forces, bending stresses or shear stresses, ultimately bending stress and shear stresses are generated, but they decay, they vanishes very rapidly when we go away from that corner or a joint. So, that is why we say that it is a local effect. So, near the juncture it is high, but as you go away, so it vanishes very rapidly. Sometimes we called it is a boundary effect. So, moment shell theory is used to find out the boundary effect at the junctions. Next, that because of small thickness, a small bending moment may cause a large stresses in the cell. Already I have told that analytical solution is possible for some typical cases. So, therefore, that if we are interested to find out the solution, then we have to go for a approximate or a numerical solution. These days you may say that finite element solution, or in general we will say that numerical solutions. So, let us say for the case of moment shell theory, so general equations in a case of circular cylindrical shell can be expressed like this. So, ultimately these 5 equations can be written into a 3 equations by using the concept of Q1 and Q2 from here and substituting here. So, this gives you the third equation. So, first equation, second equation and third equations. So, we can use that concept of Q1, Q2. So, ultimately we will have a third equation. But we cannot solve, means we can solve it, but we cannot solve in terms of a moments. We have to convert in terms of a primary variables. So, we have to find out the value of N11, N12, M11, M12, M22 in terms of U, V and W, then we can substitute it here. So, that is why it is difficult. So, getting all these terms. So, ultimately very simple solution, very example I am going to solve it here, that axisymmetric bending. For that case, that deformation is independent of theta, and nx theta, mx theta and q theta considered at 0. So, if we take consideration of this, so ultimately this gives you these 3 equations, very first equation, second equation and third equation. So, from third equation Q1 can be written as M11 comma x, and if you substitute it in this equation, so this gives you a second equation modified, and first equation is like this. So, first equation can be directly find out that N11 will be minus of integration of q into dx and plus some integrating constants. But from third equation, if you substitute all these things, that we can solve from the second equation. Now, what is the definition of epsilon 11, epsilon 22 and curvature for this case, because for cylindrical case and axisymmetric case. So, derivative with respect to theta is going to be 0 and V is absolutely going to be 0. So, if we choose all these things, so strain components are expressed like this. Now, the N11 can be written as Q11 into epsilon 11 plus mu times of Q12 and integrating. So, if you do so, it will comes EH1 minus mu square and this thing. Now, we say that Nxx is going to be 0. So, from here du comes minus mu times W by R, and N22 expression is this. If you substitute this expression here, That gives you expression of N22 is minus EH by R into W. So, ultimately we are expressing all the variables in terms of a transverse deflection W. So, moment will be d times of W comma xx, M22 will be minus d mu times of W comma xx. So, if you substitute in that second equation, it leads to a fourth order differential equation in x. So, this equation will have, can be solved, and we can say that there will be homogeneous solution and particular solution. So, homogeneous solution will be when this is equal to 0. So, we can assume a homogeneous solution like e raised to power of kx. If you substitute it here, so d k raised to power 4 plus E h by r square equal to 0. So, for finding out the roots nicely, so we multiply with the h and divide by h. So, basically we can assume this is alpha 4. So, ultimately equation becomes k 4 plus 4 alpha square. So, we can write equation like that, k square into 2 alpha square ka whole square equal to 0. So, we can say that k square plus 2 alpha square is equal to 0. Then k square will give you minus of 2 alpha square. Then k will be 2 of iota under root 2 and alpha. So, plus minus. So, in this way there will be 4 roots. Second, so 2 roots will be same and there are complex roots. So, the solution can be written as e raised to power of alpha x k1 cos alpha x plus k2 sin alpha x plus e raised to power of minus EAX k3 cos alpha x k4. So, k1, k2, k3, 4 are unknowns. It is a fourth order equations. So, there will be 4 roots. So, we can solve the 4 means 4, we need 4 boundary conditions. So, we can solve maximum 4 variables. And what will be the particular solution? So, particular solution can be written as basically depend upon a function of Q3. If Q3 is sine, then the particular solution will be different. Now, we have assumed a UDL. For that case, it will be QR square upon my EH. The boundary conditions, so if a shell is built in means clamped, then we say that W is 0, W comma x is 0. Basically, x is 0 and x is equal to L. So, we will have a fourth boundary condition. So, we can solve K1, K2, K3, K4. Then for the case of simply supported, deflection is 0 and moment is 0. So, from their moment ultimately W comma double derivative is going to be 0. Similarly, when the shell is free, the moment and shear force is 0. So, the expression of moment gives you del W by double x and triple derivative of x is 0. So, by following this boundary condition, we can solve them. Then the next, as of I would like to say the D case, when shell is loaded with the Q naught and M naught, because at the edges we can say there is some shear force is applied and moment M naught is applied. So, for that case D moment Mxx equal to applied moment and shear force equal to applied shear force. So, in this way we can solve the problems. I have explained that membrane shell theory and moment shell theory. The one can do the application part. The details are given in any thin shell theory book. The next I am going to provide you a general solution, that how to solve a general cylindrical shell for a simply supported shell. So, in the next lecture I will explain the basic solution of a cell. Thank you very much.